All right, so last part 3 of section 5.1. Right, so now we're going to be talking about driven motion. So this is no longer free motion. This is where we have an external force, lowercase f of t, acting on the mass in addition to the gravity in the spring, right? And also the viscous force here, right? So, right, so you get this equation, and dividing by m, we get this equation. So capital F of t, this capital F of t here is really just the lowercase f divided by m, right? Right, and so we're going to consider this capital F to be sort of the applied force, even though it's really the force divided by the mass. It's, yeah, I guess it's really the acceleration then. But we're calling it capital F, right? And typically this capital F will be some sort of a sine or cosine function, although it doesn't have to be. But in most of the cases it will be, and I think in this example it will be, right? So this capital F, of course, provides the non-homogeneous term for the differential equation. So in these examples here, we're going to have to be solving non-homogeneous differential equations, which means we're going to also, in addition to finding the complementary solution, we have to find the particular solution. Okay, so let's get right to the example here. This is number 34 in section 5.1. We have a mass of 1 slug attached to a spring whose constant is 5 pounds per foot. And initially the mass is released 1 foot below equilibrium position with a downward velocity of 5 feet per second. All right, so let's write that down. These are the initial conditions here, right? So x of 0, the initial position is going to be 1 foot, and it's downward, so it's positive. And then the initial velocity is also downward, so that's also positive, and this is going to be 5 feet per second. Okay. Subsequent motion takes place in a medium that offers a damping force numerically equal to twice the initial velocity. And so if you remember what that means, it means that the force is just 2 times x prime. That's the damping force. So beta here is 2, right? Beta is 2. And so what does that mean for lambda? Well, remember, lambda is beta over 2m. Sorry, that's a beta. So this is just 1 over m. And the mass is 1, which is 1 slug, so lambda is just 1. All right. Sorry, that's a beta. Okay, so with that, we have our equation. In fact, m is 1, so either equation, you get the same thing. We get x double prime plus 2 times lambda. 2 times 1 is 2, so 2 times x prime, plus either k or omega squared. In this case, I think they're the same. So what is k? K is either m omega squared. Do they give us k? Oh, yes, k is 5. Yeah, I'm sorry. Oh boy, k is 5. That's given in the problem. The spring constant is 5 pounds per foot. All right, so k is 5. Right. And since m is 1, k is the same as omega squared, which means omega is the square root of 5. So I just realized I messed up the k here. K is just 5. There we go. Equals 0. Okay, so far. All right, so now we solve this equation, and I know I missed a minus sign last time. Again, apologies. I actually had it wrong in my notes, so I just copied it wrong. And so why don't, well, right, we're solving the auxiliary equation, r squared plus 2r plus 5 equals 0. That's a 5. And so I'm going to actually solve this by completing the square. You take away 5, and you add 1 to both sides. you get that r plus 1 squared is equal to negative 4. And when you take the square root, you get r plus 1 is equal to plus or minus 2I, which tells me that r is just negative 1 plus or minus 2I. So I'm not going to miss the negative sign here. Right? So I think we can translate that pretty quickly into the solutions. X is just going to be e to the negative 1, negative lambda, right? So negative 1 times t. So e to the negative t times c1, or we could do the amplitude, but I'm gonna do c1 times cosine of 2t plus c2 sine of 2t. So once again, we are in an underdamped situation because we do get sines and cosines here. Okay, right. Oh, I should remind you that we're solving the homogeneous version here, right? So this is the complementary solution. This is xc for complementary, and that solves the homogeneous equation, right? If you notice in part A, we have an external force here, our little f of t, which is in this case is the same as capital F because m is 1. Thankfully, m is 1, so that makes this easy. Right, so our general solution, x of t here, is going to be, well, the complementary solution, xc, plus the particular solution, which we still have to find. Right? So we know what xc is. Now we look for the particular solution. And remember, it's based on the non-homogeneous term here. So we used to call this g of t, I guess, but now it's f of t. So we have 12 times cosine of 2t plus 3 times the sine of 2t. Okay. So our particular solution should have the following form. It's just going to be a times cosine of 2t plus b times the sine of 2t. If you're thinking, wait a minute, don't I need to multiply by t because don't I have this in the complementary solution? No, we don't, right? Remember, this is e to the negative t times cosine of 2t, right? There's no conflict. There's no duplication here. We don't need another t here, right? So because of this, there's no duplication between the complementary and the particular solutions here, right? So luckily, in this case, because of the e to the negative t factor here, that's an entirely linearly independent solution to just cosine and sine of 2t, right? So yeah, we don't, right? So we're in luck here. This is our form of the particular solution, right? We don't need we don't need to multiply by t or t squared or anything like that. Okay, great, right? So now what do we need to do? Well, now we just need to plug this in the original equation. Obviously, the original equation here, the 0 is going to be replaced by f of t. But for now, let's just take the two derivatives. So xp prime is going to be negative 2a sine of 2t plus 2b cosine of 2t. All right, and then for the second derivative, sorry, this is prime, right? So xp double prime is going to be negative 4a times cosine of 2t, and then minus 4b sine of 2t. All right, so now just plugging them back in the original equation here, x double prime plus 2x prime plus 5. Do that here. So x double prime p plus 2 xp prime plus 5 times x. Oh, I did forget the x here. Oops. Of course there's an x. Sorry about that. So, yep, that means there's going to be an x here as well. 5 times x equals, well, actually it doesn't equal 0. Remember, it's going to equal the f of t, right? The 12 cosine of 2t plus 3 sine of 2t. Okay, so what's this left side here? It's going to be all of this. And, well, we know that one term is going to involve a cosine, the other term is going to involve a sine. So I'm going to try to do this all at once. Well, at least I hope I can do this all at once. Right. So on the right side you get, oops, 2t. Sine of 2t. All right. So what do we get on the left here? So x double prime, for the cosine, we're just going to get a negative 4a for the double prime part. For the prime, 2 times xp is going to be 2 times 2b, so that's 4b. And then in the original x, we get 5 times x, we get 5 times a, plus 5 times a. All right. And then what about the sine terms? So for x double prime, we get the negative 4b sine of 2t, so negative 4b. And then for 2 times xp, we're going to get 2 times negative 2a, so that's negative 4a. And then plus 5 times x, 5 times b here. Okay, so is that more or less clear? Doing this all at once here. So let's see, simplifying this, we're just going to get a plus 4b times cosine of 2t, and then plus, let's see, negative b minus 4a, so I'll put negative 4a minus b. Wait, 5 minus 4 is 1, plus b, right? Times the sine of 2t. So that has to match what's on the right. So this gives us our system of equations here. So a plus 4b has to be equal to 12. And then negative 4a plus b has to equal the 3 in front of the sign. Okay, so I think that's right. So let's see, we can solve this system if we just multiply the first equation by 4. Multiply this by 4 on both sides, and that gives us, let's see, 4a plus 16b is equal to 4 times 12 is 48, and then negative 4a plus b is equal to 3. When you add these, you eliminate a, and you get 17 times b is equal to 51. And 51 divided by 17, I think, is 3. Yep, so b is 3. And if b is 3, what would a be? So a plus 4 times b is 12 equals 12. Oh, yes, a is 0. So, right, so a is 0, b is 3, and that means our particular solution, xp of t is just going to be 0 times cosine of 2t plus 3 times the sine of 2t. So there's really just a sine term in the particular solution, right? All right, now putting this together, remember the full, complete solution is just the complementary plus the particular. So I think I can write that down here. I'll squeeze that in up here, right? So x of t is going to be this, so I guess I'll leave that alone, e to the negative t times c1 cosine 2t plus c2 sine of 2t, and then plus 3 times the sine of 2t. All right. Oh, before I box this, remember we're still not done because we need to find the c1 and c2. Right? Remember, this is an initial value problem. We have an initial conditions way up here. So we have to use these initial conditions to find the c1 and c2. So just for convenience, let me write these down here so I don't forget. X of 0 was 1, and x prime of 0 is 5. So now I have more room down here to solve this. So let's start with the x of 0. So e to the 0 is 1. Cosine of 0 is 1. Sine of 0 is 0. So this is still just c1. And then, yep, sine of 0 is 0. So plus 3 times 0 is 0. So very quickly we get c1 is 1, right? So yeah, that c1 is usually just kind of comes for free here. Obviously to find c2, it's a little trickier because we need to take the derivative. And again, it's another product rule. So instead of doing that here, because I can see this is going to take a while, let me go way down over here to take x prime of t. So first times the derivative of the second. So the derivative of the second is negative 2 c1 sine of 2t plus 2 c2 cosine of 2t plus second times the derivative of the first. So it's the second, and then you just get a minus sign here, right? So minus c1 cosine of 2t minus c2 sine of 2t. Right, oh, and then the derivative of 3 sine 2t is 6 cosine of 2t. All right, well, let's clean this up a bit. I mean, we don't really have to here, but it might make it convenient. So the cosine of 2t term is going to have a negative c1 plus 2c2. Oh, we know what c1 is. c1 is 1. So let's just make that negative 1 plus 2c2 times the cosine of 2t. And then the sine term we don't really need to worry about because sine of 0 is 0, but let's just get it anyways in case we need the velocity. So what do we have for the sine part? We have negative 2c1, which is just negative 2 minus c2 times sine of 2t. Right. And then this we can leave alone, 6 cosine of 2t. Okay, right, so that's the velocity at any given time. Now, plugging in t equals 0, we get, again, 1. And then cosine of 0 is 1, so this will be just negative 1 plus 2c2 plus 0. And then cosine of, oh yeah, 6 cosine of 0 is 6, so plus 6. And what does that equal? That equals 5, right? Okay, positive 5, yeah. So let's see, 2 times c2, 6 minus 1 is 5, equals 5. Oh, that's nice, because c2 is 0. Okay, so after all that, c2 is 0, c1 is 1, and now I can finally write down the complete solution. Actually, I'm going to try to do that here because we can erase the c1 and just put a 1 here. And in fact, c2 is 0, so this part goes away. That becomes 0. And okay, so maybe I will write it down again here. So x of t is finally e to the negative t cosine of 2t, right, times 1. and then plus 3 times sine of 2t. So that is our final answer. Well, at least for part A, I think. Oops, it's no prime here, right? So part A, find the equation of motion, and, well, we did that. So that's x of t, and so that tells you the motion after t, or at any given time. It tells you the displacement from equilibrium, right? Okay, so parts B and C just have to do with the graphs. We want to graph the transient and steady state solutions on the same coordinate axes. So what do they mean by transient and steady state, right? So steady state, you can imagine, is just the sine and cosine version. In other words, it just kind of goes back and forth in a steady way. The transient means the part that goes to zero, right? The part that quickly drops off exponentially, right? So I think just looking at the form here, the exponential term, because it's e to the negative t here, this is the transient term, and then the sine part, that's the steady state. Right? So what happens if, as t gets bigger and bigger, the e to the negative t quickly goes to, well, I don't know about quickly, but it'll eventually go to 0, leaving you with just the sine part, the 3 sine of 2t. Right? Now, when t is small, like when t is 0 or 1, or right, then this exponential part dominates, right? So then that's the transient part. But as time goes on, the transient part becomes less and less significant. Okay, so for part B, we want the graph. That's not good. Let me see if I can do a very rough graph here. So this will be my time axis. This will be the displacement. And so here's where you have to be careful. I think I'm going to go by the usual convention that up is positive and down is negative. Now, of course, that's the complete opposite of, oh, I didn't draw the spring. Okay, good. So basically, this going up is down and down is up here. But I'm going to draw as if up is positive. So basically just stand on your head, and then that's the motion of the spring. But yeah, because in graphs, right is positive, up is positive. So all right. So if we just graph the transient parts, so we get e to the negative t. So that might look, I'm going to start way up here, that might look something like this, right? But it also does involve a cosine. So in other words, it might go sort of back and forth like this, right? And then eventually taper off as t gets bigger and bigger. Okay, so this is the transient part. And then on the same coordinate axes, they want the steady state part, which is just sine of 2t. And then the eventual amplitude will be 3, right? So I don't know where 3 is on the scale here, but I'm going to put the 3 here. So the steady state will look something like this. Oh, sorry, I don't mean to taper it off. Let's try that again. This is really hard to do, right? Okay, so that's the steady state version. And so the actual solution will just be the sum of these two things here. It'll be the sum of these two things here. And so even though initially the transient part is fairly significant, and by the way, when t is 0, this is 1. So actually, I take this back here. The transient part really looks more, can I do this in green? Really looks more like this, right? Because even when t is 0, this is just 1. Not whatever this is. This is like 5 or 6. So So the transient part is actually a very tiny component of it. So you can imagine the complete solution, the complete graph here, graph the equation of motion. Oh gosh. All right. It's basically just the red graph here. What color should I use here? How about purple? So it's basically just the red graph, but lifted up one unit here, right? So it's going to be something like this. It's going to start a little bit bigger and then get a little bit smaller, but eventually it's going to look just like this red graph because you can see the transient part is almost zero at this point, at this stage. So yep. So it starts out at 1 a little bit and then goes maybe a little higher than it would be, and then it settles down to the final amplitude here is 3. So it might overshoot the 3 a little bit here, but eventually it will just settle down to 3 as the amplitude. And so why is that, right? So if you were to write this force function here, I imagine in terms of the amplitude would be 3, right? Just in terms of the sine part here. So again, that being the steady state version of this is the part that dominates as t gets bigger and bigger. And so, right, so yes. And in fact, you could approximate the period, of course, because omega is 2. That means the period is 2 pi over omega. So the period here is just pi. So from peak to peak here, it goes back and forth every pi seconds. I mean, yes, that's approximate because the transient term does affect that slightly, especially in the beginning, but over time it has a negligible effect. So I think that's it for this question here, and that takes care of driven motion. So I should mention there's one more topic in this section 5.1, and that's what happens when there's no damping, but there is a driving force. And I'll let you read that. It's a perfectly good section in the book, having to do with what's called resonance. So when you have a driven motion, but either no or maybe a very weak damping force, you get something called resonance. And at some point I'll post my notes. I have some corrections to make, and my notes, of course, are always a work in progress. But eventually I will post those notes, and you can read it there. But it's basically just the notes from the book. So again, resonance is a very interesting topic, but one that I'm not going to get to here.